Hi everyone, welcome to the class, the weekend batch, and good morning everyone. And let's start. In the last class, we did the basics of Linux. So we understood the Linux commands, couple of Linux commands which are required for our analog layout course. So we get gone through over those things. I have shared you the PDF of the Linux command so that you guys can be familiar with. I hope you have understood that Linux session and understood that whole command sets, and you have might have practiced in the over the week. So can you guys confirm, is there any doubt in over the Linux commands? Is there any doubt in the Linux commands? Can you just guys that one? Hello.
Hello.
Yeah, tell.
Sir, that some part of the video is not moving forward, sir, in that video.
Mm, okay. So like any issue is there in the video, right?
Yes, sir.
Okay, I will check that one. I will check that one. I have seen that issue actually, and that might be some encoding issue might be there. I will look into that one. Okay,
Okay, sir.
I will look into that one. Okay. So any issue in the Linux command sets on understand the Linux commands? Arshad, is there any issue for you understanding the Linux commands?
No, sir. Only that some part of the video is not moving forward. No, that's why it has stopped, sir.
Okay. I will check that one. Okay.
That's
That
it, sir.
might be due to that something sometime happens with the Microsoft. So some due to some server point of issue, they happen actually. Okay,
Okay.
so someone messaged me. Let me check. Okay, so who's this guy? Okay, okay. Rohit is not available in this one. Yeah. Hi, Rohit. Okay, so VMware the purchase. Okay, in this one VMware player, there would be an option while installing. There was an option. Can you share the screen that I can help you out immediately? It's a quick solution. Can you share your screen, Rohit? Let me help you out. Hello. Okay, he might be not audible. So, okay, yes, share the screen. Go to the VMware installation, that one VMware installation. Let me help you out. No, yeah, what is that password? Not this one. Only the VMware. Yes, wait, 1 second. Top one. Yes, continue. No, man. Do the top one. Use VMware. Yes, and continue. Select use. Yes, continue. Yeah, it is running. Na? What is the issue? You can just go and so remind me later. Remind me later. Yes, open virtual machine where you have downloaded the cadence file. Go there. Simply go there where you have downloaded the cadence file actually. Excuse me. You have to extract this one. You have to extract this one. Right click. Okay, 1 second. Right click that one. Cadence virtuoso. Wait. Open with. No. Open with WinRAR. WinRAR. Do WinRAR. Yes. Open that one. 1, 2, 3. Type here 1, 2, 3. Enter. Okay. 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 Uh, cut out. Okay. Select that yellow one. Only the cadence virtuoso. Select that only the cadence virtuoso. Okay, and click on extract to top, extract to. No, in the yes, that one. Select desktop or download. Download only. Select. You can select. Okay, let it happen. I will come back to you. Okay, you just ping me. I will come back to you. Let it get extracted first. Okay. Okay, then everyone, let me start the class so that we can be working on the class part. Okay. Okay. So today we will be starting the cadence tool itself. Okay. So basic logic gates and implementation in cadence. Like we will not be starting scheme map, what is Boolean algebra, all sorts of things. This is understood that you guys already know what is digital electronics. Okay. What is K map and all sorts of things. Okay. So we will be using these digital gates to understand our, we'll try to understand our cadence tool familiarization is required, because if the tool familiarization is not available, is not done at this moment, it will be difficult for you to go forward and understand the analog layout, actual analog layout. Okay, so tool familiarization is very much required. So for this one, learning objectives are implementing each type of gate in cadence for becoming familiar to tool. We will be implementing combinational circuits in cadence. Some you will implement, some you will be working in your task. Okay. Mm, okay. So some of the logic gates we will be implementing here, which are logic gate building block of digital circuit. You all know this one. This is basic definition. And in logic gates, we will be implementing AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR. These are all even NAND in logic gates we all have in our system. Okay, so we will be, so that we will not be following the standard cell concept for now. We're not. We will just only try to figure out this how to implement. We are not following any standards. If any guys know what is standard cell design, please don't put that one, because the standard cell currently we are not doing. Means do standard cell later, but for now we are actually working on the and how the tool works, what are the flow, what are the options, how to do the tool properly. So that is the thing we are actually going to work here. Okay, so excuse me. So in this one, first we will be start with the not gate inverter. First we will start. First we will start with the inverter. Then we will gradually go to NOR gate, NAND gate. Then some couple of circuits, big circuits will take care. Okay. So first we will start with the NOT gate. Okay. So let me go to the cadence virtuoso. So before me tell you, let's draw the circuit here itself only. Okay. Let's draw the circuit. So for the NOT gate, what I will tell you, let us draw the stick diagram first. Before, give me 1 second. Okay. So, like how to draw before when you are drawing a digital gate. So you have to first draw a stick diagram. That's the basic you should be knowing. Okay. So how it is being done? Let me show you. So how a PMOS and a NMOS is required. Inside this one, this is a symbol. Inside this one, the actual circuit is there. Okay. So first it starts from, like, two things are required. Let me show you. One pull-up network and a pull-down transistor. Sorry, this is a pull-down transistor, the pull-up, and the below will be pull-down. Okay. Down. And this will be the pull-up. This is a pull-up transistor, pull out between it is being shorted, okay, to making a even making a CMOS. Okay, and this will be a VDD line for us. This will be the ground line for us. This will be input pull up. This will be for pull down, in where we will be shorting these both the inputs for a inverter part. So we will make it like A here, okay, and from below this output. The overall block structure of CMOS circuit diagram. After this one, we will come to the circuit actually. Okay. For the circuit, what we will do, we will take a PMOS first. So first thing, when there is a plus operator, okay, when let me tell you one thing, when the plus operator, okay, when there is a plus operator, means when there is a NOR operation will be there, then the PMOS becomes, okay, the P in the plus operator. Again, someone is there actually. Let me add him here. Rohit, you can join, rejoin. It would be good. So, any other guys facing voice issue? Can you confirm? Other guys are facing any voice
Um,
issue? That voice break.
in between, it is breaking
Yeah, hi
actually.
Mahesh.
Yeah,
Is it breaking?
yeah, in between it is breaking.
Let me do one thing. Wait. I think due to the rain, actually, this sometime happens. 1 second. Please give me 1 second. Let me change the network once.
It
That would be
some
great to do.
otherwise it's fine. In between it's breaking sometime.
Okay, okay. Let me change the network. That would be great to do. Think so. I think now this should be okay. Yeah, is it okay now? Hello.
Yeah, it's fine.
Okay, okay, okay. Let's start. Let's start. Okay. I will come back to your extraction thing, Rohit, at last. Let's continue this one. Okay. So here, if we come and we try to check this one. So first we will be taking this inverter. Okay. This inverter guy. Okay. This inverter guy, a P. So I am teaching this plus operator. In plus operator, when it's a NOR operation, like in NOR gate, we do plus operation. In NAND gate, we do dot operation. Okay. So basically, if you ask me, first in the first step, we directly don't draw the NAND gate, sorry, AND gate or OR gate. AND gate and OR gate is built from the NAND gate and NOR gate itself, okay, using an inverter. So basically in CMOS, first NAND gate, NOR gate and inverter can only be built, okay, in the CMOS. Okay, it's a normal in PMOS, NMOS, wherever you go, the basically NAND gate, NOR gate and NOT gate inverter can be built. With this one, in a NAND gate, if you put an inverter, it will become AND gate, and in a OR gate, if you put a NOR gate, if you put an inverter, it will become OR gate. Okay, this how we can build AND gate and OR gate. So in normal pen paper, we can draw the AND gate and OR gate. So, but in actually physics, actually in practical, first NAND gate and NOR gate and inverter is only drawn. That's why NAND gate and NOR gate is called the universal gates. Actually, with that NAND gate and NOR gate, you can build any kind of structure of logic circuits. Okay. So, in if you many times you will see there will be no AND gate, particularly using a NAND gate. They will not make a even in with NAND gate they will make a AND gate, but they will use that not even that inverter separately. They will combine that NAND gate itself and they will convert into inverter. If we short the inputs of a NAND gate na, or NOR gate, it will act as an inverter. Then we can put it in front of a NAND gate or NOR gate. It will start working. Then it's possible to do. Okay. So in plus operator, PMOS works in series connection. Okay. PMOS become series connection and NMOS becomes parallel. Okay. Okay. It become parallel. So the connection is like this one. Okay, let me show you. This is a PMOS. Okay, if two PMOSes are there, then it will become kind of this. Okay, it will become kind of this in time of plus a series operation. PMOS, this is a PMOS. Okay, and when it is in parallel, NMOS will become like this kind of thing. Okay, it will become like this kind of thing. Okay, this kind of thing. Okay, so if we combine both these two, na, it will become a NOR gate. This is actually, it's a NOR operation operating. This operation, if you are seeing here, it's a NOR operation completely. Okay, when we combine both PMOS and NMOS together from this point to this point, it will become a CMOS structure. Then it will become a CMOS NOR gate. Okay, so this is the style of the NOR gate actually, in which PMOS, you should remember, when plus operator, PMOS should be series, and NMOS, then it should be parallel in plus operator. But when you come to dot operator, when you come to dot operator, the PMOS becomes parallel and NMOS becomes series. NMOS becomes series. Then if PMOS is parallel now for us, if PMOS is parallel now for us, then what will happen? It will, this is the parallel of PMOS, and NMOS will become like this. Okay, NMOS will become like this. Then if we combine both this guy, if we combine, let me highlight it like this. Let me highlight both of them like this actually, then it will be easy for you to understand. So this should be, and then it will become a NOR operation. Okay, it become a NOR operation. And if we consider this one, if we consider this whole guy, actually, if we consider this whole guy, okay, then it becomes a NAND operation. Okay, this is a NAND gate actually structure. This structure is the NAND gate structure. Okay, so you have to remember this one. It's a very basic of the CMOS design. Okay, when it is a plus operator, PMOS becomes series and NMOS become parallel. When it's a dot operator, the PMOS become parallel, NMOS becomes series. You have to remember when you are designing any kind of circuit. As a layout engineer, you don't have to make any circuit design. Okay, so circuit designer will be responsible for creating the circuits for you guys. You will just getting the circuits. You will be applying the, you have to understand the critical points of the circuits, and you have to do the layout. Okay, steps of the layout there are you to follow. So many floor plans, then floor planning, placement, these all things are there. We will come to those things later. Okay, these are basic you should be knowing. But in now the inverter, actually when it comes the inverter, if you see, this is the basic thing you should be knowing. And this part is drawn from the block diagram for the inverter. Okay, so in the inverter, one PMOS is required. Okay, one PMOS pull up network. Okay, so this should be VDD. Then NMOS is required. Okay, and this should be the ground. Then if we short as per this block diagram, okay, A, and then we take this as a Y output. So this is the circuit, CMOS circuit of the inverter actually. Okay, so this is the CMOS circuit of our inverter guy. Okay, so we will able to understand this CMOS circuit using a small stick diagram, how it should look in a layout part. Okay, how it should look in a layout part, we can try to understand that thing. Okay, so let me show you the stick diagram once. So let me erase it, this one a bit. Let me erase this one. Okay, let me erase, I'm erasing this one for now. Okay, so let's try to make the in block diagram. Okay, so for block, sorry, stick diagram, what happened? We take some couple of colors. Okay, so for the VDD line, if we consider this is a VDD line. Okay, so VDD should be blue color. VSS should be blue color. Okay, this is VDD. This, let me write it as a VDD, and this should be sorry, one second. This should be VSS. This should be VSS actually. Okay, it should be VSS. Okay, the VSS. Okay, In between this one, we will be try to make the our stick diagram. Okay, we will try to make our stick diagram. Let me make it bit thicker so that it will be visible for you to understand properly. Okay, after this one, what will happen? We will be taking the yellow color, which is considered as a P diffusion. So these are some kinds of layer. I will tell you this layer in the layout also. Okay. So for doing the stick if the in an interview, if any interviewer asks you, okay, you have to either use a different color in the paint to draw this one, and if you are drawing in a copy with pen and paper, you have to mark those regions as P diffusion, N diffusion. You might don't have a color. Then what you will do, you will just simply draw the stick diagram and you will just mark it that sir, this is a P diffusion, this is the N diffusion, this is the polysilicon. You have to mark them just. Okay, let me show you. The the metal connection is indicated with blue color. Okay, then the P diffusion, P type material diffusion is indicated with yellow color. If you come across, it should be a yellow color. Okay, it should be in yellow color. Okay, and then the in diffusion is also there. Okay, then the in diffusion also there. So below, so PMOS is in the top, so we did P diffusion in the top. N diffusion, N type material, N type transistor is in below, so we will do the N diffusion below. Okay, so we do the N diffusion in the below part. Okay, after we did the N diffusion, see if we see here, this is a source, this is a gate, and this is a drain for the PMOS. Again, for the NMOS, it's drain, gate, and a source. Okay. So what's happening? The drain and drain is being connected. For PMOS drain and NMOS drain, both are getting connected here. Okay. So if you see here, we have done the connection. So if we check this part, if we check this part actually, okay, if we let me put a mark, so it's a connection part. Okay, so if so it should be our source, this should be also our source. Now we have to do, we have to connect the drains actually. So for connecting the drain, we don't use any other thing, we use metal connections, our standard metal connection which we use for VDD and VSS. Okay, so what we will do, we will be drawing a metal connections between the drain connections. Okay, like this drain connection, I will draw on metal connection and I will take it outside. Okay, simply I will draw a metal connection between the both drains, both to connect this PMOS and NMOS drains. I will use a metal connection only. So we use metal one only because it's a basic metal for the higher nodes. If you go in the lower nodes, it will become M0 is also there. Okay, so here it's a 90 nanometer, so we are using maximum minimum metal is M1. Okay, minimum metal is M1. After this is done, P diffusion is done, N diffusion is done. We have connected both the drains and taken the output outside. Okay, so this should be our, let me write it. So this should be our output Y. Okay, output, and we should, let me write here, drain and the drain connection. At this part we have done. Now we have to connect the gate connection, which is this guy, this gate connection. Okay, actually a gate is indicated with red color. Gate is actually called polysilicon. It is called polysilicon. The material is polysilicon. Okay, so that why we make the gate connection with polysilicon. So we have to draw one red color thing here. Okay, one we will draw one here, gate connection, and then after that we will again drawing a metal. We cannot in the layout, you should not actually do any kind of routing. You should not do any kind of this kind of routing with only whatever the polysilicon coming default from the layout. That should be your maximum polysilicon use. You should not route the whole block with the polysilicon itself only, because polysilicon itself is a very high resistive material. If you draw that one, then there will be voltage drop and the delay will be created in the device. Okay, so you should not do that one. Okay, so just it's a normal connection. Just I will tell you in the layout. So just draw the polysilicon connection, then just simply draw the metal over this one. You have to just draw a metal over this one, and simply this will be your A connection. Let me write the A connection here. This should be your A connection, and this is a point connected. Okay, so this should be actually your stick diagram. This is how the stick diagram of a inverter looks like. Okay, so you have to mention there. So source, this is source. Okay, let me write it for you also. So the blue one is the VDD. Okay, let me, so the blue one is the VDD connection. Yellow one is called as P diffusion. Let me write it for you also. It will be easier. Okay, so let me write it somewhere here. Okay, let me write it here only. So blue one is the metal one connection. Let me write the metal one connection for you. So this should be the metal one connection. Okay, metal one. Okay, and this is also a metal one. Metal one. Blue one is the metal one. Remember. Okay. Now come to the red one. This guy. Okay, this is called polysilicon. This is called polysilicon. Lyicon. Polysilicon, or you can say it is a poly also. Okay. Then it comes to the yellow part. So this yellow one. Okay. Let me write it like this. It is called P diffusion. P diff. Or I'm writing a P diff here. Okay. It's a P diffusion. Okay. Then come to the green part, which is the N diffusion guy of our. So we will write here N diff. Okay. N diff. So this is how the stick diagram of a inverter looks like. So when we will be doing our layout also, it will be look exactly like this one only. The stick diagram only, bit of orientation change is there, but it looks overall should be looks like the stick diagram only. Okay, so you should be familiar with
So
the
here,
stick.
like both gates are also should be connected with metal only, right? Here both gates are joined with the polysilicon.
No, actually, in
Here,
the stick diagram, actually, if you ask me the stick diagram, actually, you are correct, actually. But generally, in the stick diagram, we are considering this point actually as a gate. Sorry, with the metal one we are considering. But actually, if you ask me, the gate should be up till this point only. Let me show you once. The gate should be maximum up till this point only. Okay. Coming from this point to this point, it should be up till this point. Again, from this point to this point, it should be up till this point. Okay. But in the stick diagram, general practice it is they generally do it normal like this, then they connect it with a gate. But in the optimized layout, you will see maximum the whatever gate available from the device itself only, that will be that part. The rest part what it is drawn, it will be drawn with a it will be drawn completely with a metal. They will not we should not use any kind of extra poly layer here. Okay, so actually you have pointed out correctly, but we actually should not draw. But in the stick diagram it is done, but in the optimized layout it is not done. We generally do it directly
okay.
from the metal, because it's a high resistive material. Na? If we do it a bit longer, the delay will be changed. Of course, if suppose you are drawing a ring oscillator, like who put the question? Can you? I'm unable to see his name. Can you tell me the point?
Yeah, yeah. This is Mahesh. Mahesh.
Yeah, Mahesh. I think you are familiar with the ring oscillator design.
Yeah.
So
Yes.
you
Yes.
will
Yeah.
be knowing the delay constraint. Okay. So if the
Mm-hmm.
delay is bit higher, so then I need a delay of suppose of 1 nanosecond. Then if I make a delay, the voltage, the resistivity changes. Then what will happen? What IR drop will be there. So IR drop will
Yes.
there
Yes.
means
Yeah.
what, the delay will of course change. If the delay changes, if I need 1 nanosecond, then it should be become like 1.2 nanoseconds. I don't need that, na. So that is the reason
Yeah. Yeah.
we should not actually route with the polysilicon, but in the stick diagram, it is drawn this like this only. Okay.
Okay. Okay. Okay. Okay.
Okay. I will tell you the layout. Okay. So this is the overview of the stick diagram actually. Okay. So this is how what we
Okay.
will be directly drawing over the layout today, the inverter part. So this is the inverter part, and this is the stick diagram. This is how our layout will looks like. not exactly doesn't look, because layout is done in more optimized fashion. So a bit of a kind of 90% it will look like the stick diagram only, because stick diagram is very essential to draw the points how the connection will be done, because many times in the layout the guys get confused. Okay, everyone. Okay, let's go to the layout first, and let's understand the overall concept. So till now, is there any option here? Any problem is there? So is there any problem for you guys to understand? Can you repeat again? Hello, Harish, Arshad.
Yeah, no issues.
Okay,
No
okay,
issues
okay.
about it.
It is clear to you, Srikant, Rohit, Pratusha. Pratusha is new today.
Yeah, yeah.
Lohit. Okay, okay, okay. So let's go to the
Uh,
layout
I
first.
have a doubt. Excuse me. And
Yeah, yeah,
Rohit.
yeah. Tell.
Yeah. Aren't we using the Euler trial method for the the layouts in the stuff?
Can you repeat again? Actually, you have messaged the
I mean,
question also.
yeah, yeah.
Uh,
Can you please?
we following the sorry, we can for layout. Aren't we are following the Euler's trail to avoid diffusion break? No, actually, in the basic level, we how you will do the diffusion break. We can in inverter the diffusion break is okay, na? Then what is the issue? I think so. Diffusion break is a problem. Oxide breaking is not allowed. Diffusion break can be done in the, because PMOS is if two PMOSs are there, then we can add the diffusions. But in NMOS and PMOS, I think we cannot do. We are not able to do the diffusion adding. That we cannot continue the diffusion directly. Hello.
So what about the complex circuits like the PCR or LDO or A to D converters, so the layout
Mm-hmm.
and stuff. There'll be a breaks in between the circuits, right? I mean, lesser the I mean it is all about the performance and the power, right?
No,
So it will have.
actually, when we do the layouts, there is a concept called matching. I think you will be knowing transistor matching. In that transistor matching, those complex circuits are mainly made to avoid the wall proximity effect and polyething. We do and process variation. We try to make the matching part. Actually, for the process variation only, we do the matching part. So in that one, we try to keep the oxide continuous. When the oxide is continuous, then there will be no breaking actually, because the oxide itself is only continuous in PMOS or it's in NMOS.
I mean, the time constraint, right? I mean, not the time, not about the timing constraint. It's about the delay constraint. So when we break, when a diffusion break is occurred, and there'll be a 2 gate delay, right? That is the reason I'm asking you. If there is a diffusion break, obviously there'll be a 2 gates of delay as I know. I
Yes,
don't know.
you are correct. So if there is a diffusion break, there will be a delay. But how the PMOS and NMOS you will join the diffusion? That's not possible, na? How the PMOS can be
Yeah,
joined,
yeah,
but
yeah,
PMOS NMOS can
yeah,
be
yeah.
joined.
That's the reason I'm asking you. Can you elaborate a little bit more on this Euler trial so that everyone will
I
get to know
will
that.
I will check this one, and I will come back to you by tomorrow regarding this delay consideration. I need to check back. Actually, we generally don't do the PMOS and NMOS diffusion. We do not make continuous. PMOS can be done, but same because same parasitics if it is. But PMOS NMOS it is not. I don't think so. I never seen that kind of thing. So PMOS, NMOS, I think we cannot do the diffusion continuous. I need to check that one once. Okay. I will check and I will let back to you. Okay.
Hello,
Sure, sure,
Yeah.
sure, sure,
Hello.
sure.
Yeah. Hi, Arshad. Tell.
sir. Sir, you have not explained how to draw the layout, sir. I mean, in steps.
Yeah. That only I'm going to say. That only I'm going to say. We
Okay, sir.
only, that's the reason I drawn the inverter for you guys. So this is a stick diagram. This is how the inverter will looks like. So this is the inverter. circuit diagram. This is the stick diagram. Stick diagram actually gives you the idea how the layout should be drawn. Okay, so that is the reason that P diffusion, N diffusion, polysilicon, metal, all these things came across. Okay,
Yes, sir.
now let's draw the
Sir,
layout.
sir, we have to draw the same color, sir, as you draw.
Yes, try to, if you have a suppose in an interview when you're going, if you have a multiple colors, if you have like with the paint, if you are drawing even a paint, if you are giving online interview, you can draw. It's actually universal colors are these only. Okay, so universal color, if
Yellow.
you yeah,
Hmm.
yeah,
For
yeah,
for diffusion, we have to use yellow. For metals, we have to use blue like that only, sir. Or else we can use any different colors for
no, no,
metals like that.
actually, see, better not, because it depends. See, if the interviewer is intelligent, he or she will get to know that you are doing the correct thing. But some of the interviewers are a bit dumb. Okay, so I am not criticizing any interviewer. So, but some of the
Okay.
interviewers are a bit of dumb only. Okay, so they think that exact color only can make the guy intelligent. That every color he is doing, then he is following the same. That doesn't mean if you have a suppose a pen and blue pen and a paper, what you will do? You will be simply drawing this only. Na? Then you have to do means then you have to point out those regions by writing like this: P diffusion, polysilicon, and diffusion. Like this, you can then point it out simply. So if you don't have color, then what you have to do it that way only. But if you have a color, try to do it in paint like this kind of thing. Okay, so I think it will be easier. Why to challenge someone? Better be in a safe side.
Okay, sir.
Okay,
Okay, sir.
some interviewer comes with a bookish knowledge, so it's very difficult for to make them understand in the time of interview within a short period.
One quick question, sir. I'm sorry to interrupt.
Okay, okay.
So what is the goal? I mean, with the technology, let's say we are in 65 nanometer technology right now. What is the
Mm-hmm.
goal for uh, the layout? What should be the goal of height and width of our layout?
Okay, okay, Rohit, before this only, I already mentioned we are not going in the standard cell design actually. So it's just today actually it's a basic start. So many of the guys will be knowing the circuit design and layout a bit. So many guys are like they don't know anything about the layout. So if I tell them everything like height, width, and standard cell constraints, that how many tracks will be there, it will be like extremely heavy for them to understand. So this is just a familiarization of the tool for them, so that they should get a proper familiarization how the tool. See, in the tools there are many things. Okay, you have to, like, here first we will make the circuit immediately, then we will go to the layout excel, then there are multiple command, then there are multiple options there to transfer the schematic to schematic driven layout. We'll do from schematic to layout, we will bring the layout, then we will adjust what is peer. So there are many things to be checked out. Okay, so many guys will because I'm from experience I tell the weekday guys what we have in the in weekday batch, the whole tool familiarization took us roughly 2 weeks for them to get over with the whole thing. Now they are capable of doing the layouts, basic layouts over the tool directly. So standard cell, if I directly go there, it's difficult for other guys to understand. Okay. So we are not considering
Okay.
standard cell. So after doing, we can check the height and width, of course. But currently, we are not doing the height and width thing. Actually, we are just dumping the blocks and then we will try to connect them so that the guys should get a good familiarization with the tools.
Okay, sir. Okay.
Okay.
And one more thing, since we are, dealing about inverter right now, can you extend this to, the tri-state inverter so that it will be a very good setup for me as well?
Okay, we'll do that and try set inverter. No issue. Okay,
Thank you.
we will do the try set inverter. Uh, like step by step we will go. Okay. So if I at the first day only itself I give them a huge thing, then it will be a difficult for them to understand. Okay. So let me run the virtuoso. Okay, so guys, when you come inside this window, when you turn on this virtuoso, okay, we are inside this virtuoso terminal. Just go Linux terminal. Is a Linux GUI. Go to the terminal directly. Everything is set up for you. So everything is set up for you. So directly, so we have 45 nanometer also, and we have 90 nanometer also. Okay. So for the 45 nanometer, we will be come back later to 45. First start with the 90 nanometer. Okay. So directly if we jump to 45, it will be difficult. So let's start with the 45. So what I will do, I will be just simply going to the terminal. This is our terminal. And here I will type virtuoso and RTUOSO, virtuoso and command. This is only the virtuoso and command, and I'll press enter. I wait for some time, it will start the virtuoso for you. Okay, it will start the virtuoso for you immediately. Okay, after this one comes, already I told in the last class, this is called CIW window, command interface window. Here, this is the log file window, and this is the interpreter window, this below one. Okay, this below one, this is called the interpreter window. Okay, let me make it bit bigger. It will be easy for you. So this is the log file where this kind of log you can able to see. You will see these are many log things are coming. Whatever task you will be doing, it will be coming in the back side of this one, which is this is a log file, and this is the interpreter window. Okay, so we can do some kinds of automation if you're doing like running a skill code or a Python code. You can type here. You can just run them. Okay, so I'm not going to that in that part. So now in this one, you will see some option file, tools, option, help. Okay. So primarily, basically, you should be going to the tools first. You have a couple of options here, which is the library path editor and library manager here should be. Okay. So you should be going to the library manager directly. Okay. So this is our library manager. So this is how the library manager looks like. In the last class already I told. So library manager is has library, cells and views. Okay. So in this one, library is there, cell is there, view is there. Many couple of things are there inside this one. Okay. So this is the library manager overview. Okay. In this one, to create a library, let me delete this guy once. Let me delete it. Okay. We have made it in last class. Let me delete it. No issue will be there. Okay. Let me delete it. Okay. 1 second. Let it get delete. Okay. Now we will go to the files, new option, and we'll put on a library. So this is the library. It's we have to make a new library. So let me make it the BHARAT Bharat IC underscore weekend. Okay, END weekend. We are creating a Bharat IC weekend, and then we will try to save wherever the location. So my location is this one. I have kept it in this part. Okay, Bharat IC weekend, and then I will press OK. Simply press I will OK. Okay, when I will press OK, this pop-up will come in the top technology file for. Okay, so you have to attach that technology file, whether it is 90 or 45 or 65 FinFET, whatever it's 7 nanometer, whatever, you have to attach it. So to do that one, click on attach to an existing technology library and press OK. Simply press OK. Click go to this GPDK 90 nanometer. We are using 90 nanometer, so go to GPDK 90 and press OK. When you click OK, it will take some time, and I think it will get attached. You can check this log window actually. You will if you check this log window, you will able to see. Let me show you. Okay, so that design library Bharat and IC underscore weekend successfully attached to technology library GPDK 90. Okay, so this is how we attach the files. So to the technology files, the library. Okay. Now the Bharat IC weekend, this directory has been created. Okay. Now simply go to this directory, select Bharat IC underscore weekend, then go to files, click select new and press cell view here. Now first cell view will come as schematic cell view we will be doing, because we need a circuit for this one. So cell view, simply click the cell view, a new file option will be come in the top pop-up. So you will see the library is Bharat IC underscore weekend. This is the cell, this is the view, this is the type. What schematic type it is, wherever layout it is, what it is, you have to see. Okay. So the cell name should be inverter, INV. and we are making an inverter, so we'll make an inverter this one, okay, and we'll press OK. Simply press OK here. It will start the inverter that schematic window for us. Some guys are here very much familiar with the schematic window, so it will be easy for them to understand. Now, after coming to this part, we will just simply draw a schematic. So this is the schematic editor window. As a layout engineer also, you should know the schematic part, okay? So if this is a black screen, this is called the viewport or the canvas. Here are couple of options are there for selective selectivity option, instance selection, wire selection, pin selection, text selection. If you turn it off, that will not be able to select. If you turn on, you can select those things. Some couple of options like rotate, flip, mirror image, those things are there. So these couple of options, save option is there. These are couple of things are there, okay? So if you come in this part, this we will be requiring these 4-5 options from here, this point, okay? 4-5 options from this point, okay? This is called create instance. Create instance, this is called, okay? So this is called create instance. So this command you can press here also. You can get add instance, or you can press I option. I for India. Just click I. This add instance will come here also, okay? This is called the wire. Create narrow wire. If you want to put a narrow wire, you can use this one. If you want a fat wire, you can use the wide wire. You can use this one, okay? Then this ABC is for if you want to name that particular wire, then you can suppose many wire names have to be there, because like the wire is considered as nets, okay, in the layout. Okay, so here it should be wire, in layout it should be net connection. So that net naming is done by this part only, okay, that ABC, whatever net connection it is, because every wire doesn't have a pin, because when it's an internal signal between two devices, then it will not have a pin particularly, okay? Then sometimes we have to write this using this command, the part name, or to name the wire, okay? This is called pin connection. For creating the pin input output VDD VSS pin. So these are the some couple of options we will be using for now. So for creating instance, I will just press this red button. You can see a symbol of a MOSFET. Click on this one. After clicking on this one, you have to click on browse. Browse, then you are using 90 nanometer, you have to go to the 90 actually, 90 nanometer. And here what we need for our circuit, one PMOS and one NMOS we will be taking, okay? So we will do PMOS, PMOS 1 volt only I am taking here. Let's take a PMOS 1 volt, let's take a PMOS 1 volt here. PMOS, I will take a PMOS. Here I will come this view option. I will select the symbol. This is called a symbol option. You have to select. Otherwise, you won't be able to place this yellow guy here, yellow symbol here. The symbol you have to select. Then this add instance option, you will see a edit window, okay? So we can edit it now on the parameters W and L, or we will able to do it later also. We will do it later, okay? First, let me add the CMOS here. Just come and put a left click. It will add the CMOS. Now press escape button. You have added the CMOS here, okay? Now to add the NMOS, simply go here again, click browse, go below, sorry, go to the top. NMOS, we took PMOS 1 volt, we'll take the NMOS 1 volt itself only, okay? All thing is there. We'll just bring this guy here and we'll try to put in a perpendicular to this guy, okay? So the connection we make, it should be good, okay? Then let me put it here. Then our PMOS and NMOS has came at this view window, that canvas, okay? Up till here it is clear how to do the schematic part. Hello.
Yes, sir.
Mr.
Uh,
Sir, we have to do along with you, or still have to listen, sir?
so if you can do along with me, it will be very good. But what happen sometimes? See, I am doing this couple of many times. Okay, so my frequency should be bit different. Your frequency should be bit different. If you can match that frequency, it's very advisable. You can do it along with me. If you do it along with me, you can match the frequency, then it's very good. If you cannot match the frequency, then just try to practice in your after the class. I will try to help. I will there to help you whenever you require me for your help. Okay. So if you have the tool installed, you can try it. Who have you done the tool, Arshad? I think you have the tool installed right here.
Yes, sir.
You can do it. You can do it. No worries. You can do it along with me. No issue. If you can do it along with me, you can match the frequency. Sometime what happen, because the 2 hours very short for this kind of designs. Okay. If you start making, it's so much fun that I can start making and do it a whole long day. Okay, so what happens? So it become difficult. So that's the reason I use the term frequency. If you don't able to match, then it will take a lot of time for you to create it. Okay. So you can, if you are comfortable, you can, of course, you guys can do the schematic and the layout along with me. Or if you cannot do, then you can, the video is there. You can play and pause, and throughout the whole day, you can try that one. Okay. That's the reason the video has been given to you. Okay. Uh, okay. So up till this is clear for other guys. Hello.
Yes.
Okay. Pratusha, Lohita, Harish.
Yes, sir.
Yes, sir.
Okay. Okay. Pratusha, you are new. Might be something be heavy for you. So don't worry. I think you have seen the Linux commands basics, right?
Yes, sir. I have seen and basics are understood.
Okay. Okay. Lohita, any issue you're facing?
No, sir. That's it.
Okay. 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 Okay, let's continue. So this PMOS and NMOS done, then we can do what here is, we can go for selecting this device. Go take your mouse to this device, click on this one. This whole thick white outline will come across. Means this device is selected now. Then you can press Q. Q for queen. Here we use Q for query. Query means we are querying this device, the property. This we are bringing. Okay. In this one, you will see couple of options called multiplier, length, total width, finger width, fingers. Okay. So what is multiplier, what is finger? I will come back to you and I will tell you later what is finger and multiplier. Just for remember, we are multiplier and finger, we are using only one and one. Not we are using, we can go 2, 3, 4, 5 fingers also we can go. Currently, we are not doing that one. We are using multiplier and finger for one and one value only. Okay. We will be taking the length and width. So the length and width is not calculated. It's just a simple value. I am putting a random value 600 by 900. Don't consider this as an simulated value. Whose guys are the schematic knowledge have there. So please forgive me that these are the not calculated values. So these are just a random rough value I'm using here for the schematic itself. Okay. So when we will be doing the project, we will be try to use the calculated values. Okay. So in the length, we will be putting 600. It's a random value actually. And then the total width is there, then the finger width is there. Okay. So I will tell you what is total width and finger width. Okay. Later. So let me just type here 900. Okay. It's a 600 by 900 nanometer. Just simple. Finger multiplier is this. You can use this same value also 600N by 900N. It will be okay. Not an issue. Okay. And then just click on OK. If you press OK, it becomes W900, length 600. Okay. And then click here. Again, go to this one and make it 900. And sorry, this should be 600, right? 600, and then total width should be let me make it as a 900. Okay. 900. Okay. And it will automatically take and press OK. So we are just taking width as 900, length is 600. Okay, Mahesh and Rohit, are you okay with these values? You guys are schematic engineers. Hello?
Yes.
Yeah, it's
I'm
fine. Like maybe generally we can take the 2 times for PMOS and 1 time for NMOS. Like let us say you can consider 1800 for PMOS and NMOS is 900. It is fine.
Okay, I'm just taking it as a random value. You guys are schematic engineer, knowledgeable schematic engineers. So you will knowing the schematic much more in detail. That's why I asked you.
Yeah. Something.
Okay. So I'm just, this is a rough value actually. Okay. So now let me connect these guys. Okay. Let me connect these wires. Okay. So we can connect this wire. To connect the wire, what we will do, we'll go this thin one. This thin one we will go. We'll click on this one. We will try connecting these guys. Okay. We will be connecting this drain and drain first. Simply click on the this one. You will come here, click on left click and then bring below and press again left click. Okay. Connected. Then we will do the output connections like this. We will click here. We will go down and put here connected. Then we will be taking this below for our connections like this one. Okay. Then we can able to take this guy in the top and we'll put here. Okay. So this is will also get connected. So we are putting this as a VDD and it's for VSS. Okay. And then we will be bringing one separate connection for here for output. And then again, we will bring one separate connection for here as an input. Okay. And there is a bulk connection also. Okay. Or body connection. For PMOS, it should go to the VDD, and NMOS, it should go to the VSS. Okay. This should be the connection. After this one up till here it is done. This connection, now we'll put the pin connections. For pin connection, we will go in this black options. Okay. In this black guys, we will go here. This black connection, create pin. I'll click on here, add pin connection will be there, pin name. So we will first put the input as A. Okay. I'll put A input. Okay. And I will simply have to put the directions. What direction showing? If the input, then we have to put the input here. Okay. Then I will click again this one. I will put Y here, output. Okay. And this direction should be output direction. Okay. And I will put the direction here, output. Okay. After this one, the VDD and VSS is only left. I will click on this one. I will make it a VDD and this should be bi-directional. You can make it as an input also. You can make it as an input also actually, but this should be actually try to make it a bi-directional. Okay. Generally bi-directional is only used, but you can make it the input also. Not an issue, not a big issue also there. VDD and then we'll put a VSS. Okay. Input output and we'll put it here. Okay. If you see here, VDD, VSS is done, A and Y is done. So this how the schematics looks like. After this all thing is done, just click on the save button and check save this one. If you check save this one, it will save the whole thing for you. So if the warning, if suppose, let me tell you, suppose this bulk is, suppose I have not connected. Suppose I have not connected this bulk part. Okay. Let me do one thing. Let me delete it. This bulk connection. Okay. Okay. I have deleted this bulk connection. Suppose I have missed this bulk connection. Okay. Then what will happen when you save this one and then you check save this one? Okay. Check and save. You click this one. It will flag a warning here. One warning found. It will find a warning here. Okay. Okay. The warning means you have to check where you have actually not connected. So actually we know that we haven't connected these bulk connections. We will go here and we will connect it this part. Okay. And then we will able to see again, we do save and check save, it will not flag any error. So that means our design is perfect and ready to go. Okay. So if you want to simulate the design, of course you can simulate the design for your understanding. You can simulate it anytime. You can simulate the design. Okay. So do you guys need to want the simulation of this one also, or directly we can go to the layout? Hello? Hello?
Yes, sir. Let's
So
show the simulation. Sir.
simulation. Okay. 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 So let's take a 5 minutes break. Then we will come back and we will do the rest part. Okay. See, we generally don't do the simulation, but I should be showing you how to do the simulation, but from next time we will not do the simulation because simulation is not part of this course, because it's a complete circuit design is a different course actually. So simulation is completely different. I'm just showing you how to get familiar with this and that. Okay. So we will connect after 5 minutes. Okay. Just take a 5 minutes
Uh,
break.
sir,
Yeah, Acha,
another, sir, sir, you have not introduced all the students' names, and some of them are professionals. So
like
you have not introduced
like what introduction you want, you can tell.
all students' introductions, sir. From
Okay,
it's like some are professionals. They have worked already. Some of them are new freshers. So like
okay. Okay. So okay, let's come back after 5 minutes. Then we will keep a 1 minute of introduction. Okay. If other guys are comfortable, we can do that one. I think so. Are all everyone comfortable to introduce? Hello, hello.
Yeah, no issues for me.
Okay. Let's take a 5 minute break. Then we'll come back. Okay. Okay. Then please have a 5 minutes break. Get some refreshment. We'll come back then. Okay. Then we'll start the class. Yeah, hello everyone. Hello. Hello everyone.
Hi.
Yeah, all are back. Harish, Arshad,
Sir.
Batusha, Srikant, Lohita, Rohit. Are you all back? Please.
Sir.
Yes, sir.
Okay. Okay, then we can put one introduction. So let's start with Harish. Harish, can you introduce yourself?
Yeah. Hello everyone. I'm Harish. I have completed my MTech from IIT Kharagpur, and right now I'm working in DRDO in the ASIC development for a inertial sensor. So I'm also learning this layout for which will be helpful for the converting this ASIC what we are designing to the fabrication level. So I've taken this course to learn those skills. So this is my brief introduction.
Okay. Nice to hear you, Harish.
Yeah.
Yeah, you Arshad yourself.
Hello everyone, I'm Sheikh Mohammad Arshad. I completed my Bachelor of Technologies in the stream of Electrical and Electronics Engineering in from Andhra Pradesh. I am 2023 passed out. I have taken this analog design course. My brother's also working in this analog domain, so I have chosen. And previously, I have taken the field design course. That's it.
Okay, Arshad. Okay, nice to hear you. Yeah, Pratusha. Hi, Pratusha.
Yeah, sir. Hello, everyone. I'm Pratyusha. I have completed in Bachelor of Technology in the stream of Electrical and Electronics Engineering in Andhra. Currently, I have 6 months experience in IT. Even though I have knowledge in electronics, I have very interest, so I'm learning this course. That's it, sir.
Okay, nice to hear you, Pratusha. Yeah, Srikant.
Hi everyone. So my name is Srikant. I completed my BTech electronics communication. So I currently working on a PCB design layout. So I'm planning to do a lot of layouts design so that we like to take this course.
Okay, nice to hear you, Srikant. Yeah, Lohita.
Yeah. Hi everyone. My name is Logita. Currently, I'm working at Infosys last 2 years. Uh, Now I want to work easy side. That's why I'm take this analog layout course. Sorry.
Oh, okay. Nice to hear you. To hear you. Yeah, Mahesh, can you?
Yeah. Hi everyone. This is Mahesh. I'm working as a circuit design engineer. I have closely 9 years of experience in circuit design. I want to explore some advanced topics in like analog layout. That is the reason I joined this course. Thank you.
Okay. Quite experienced our Mahesh is. Experienced guy. Yeah,
Uh,
Rohit. Yeah, Mahesh, telling.
No, it's just
Okay. Yeah, Rohit, you can introduce yourself if you can. Hi, Rohit. Okay. I think Rohit mic is not working, some kind. Okay, so Rohit is actually just studying his master's at University of Texas at Austin. So he is currently studying these things, and this is all for the Rohit's introduction. This all. Okay. So yeah, okay. The introduction was quite good to by knowing everyone. So to know each other, the introduction is required. So 2, 3 guys are not available today here. So that's why their introduction is not available. So when they're available, then we will try seeing that one also. Okay. Okay, then let's start the session class. Where we left off, we should have done the simulation. Okay, let's do the simulation part once and check it. Let's check this one. Before simulation going, what we will do, we will first go to edit. Sorry, we'll first go to create. We'll create a symbol first for this one. We can simulate directly here also, but I should show you the symbol thing. That's the reason I am showing the symbol also. Okay. We'll first go to create, everything save done. We'll go to create, cell view, and in from cell view, then from cell view we are taking. Okay. If the cell view, from cell view, this option will come. Library is that one. Cell name is inverter. Schematic is this one. This is schematic to view name symbol. We have to create a symbol actually. Okay. Why symbol is created? Suppose we want to integrate this particular inverter circuit in some other block. Okay. If we copy this big circuit and we put there, it look very odd, like awkward. So that's the reason symbol thing has been created. So that's the reason. So it's very easy to align there each symbol. So it looks clean, proper, and quietly understandable. Because 1 second if you try to see, okay, this what kind of circuit is, okay, then you will get a circuit inverter. But if you go with the symbol, it will be much easier for you to quickly check that it's a symbol of a inverter, NAND gate, NOR gate, or a BGR, or a decoder, or a LDO, whatever it is. Okay, so that's the reason we are creating cell view. We'll go click on this one, and then we'll do okay. After the OK, you have seen left pin, right pin, top pin, bottom pins. Okay. Left A is there, right Y is there. Right pin, top pin should be VDD. Okay. Not the VSS one. Okay. Top pin should be VDD. Let me write the VDD here, and bottom should be VSS. Okay. Bottom pin, you should have to align this one properly. Okay. This top pin should not be VSS or VDD. Only VDD should be there. Left pin is A, right pin is Y, top pin VDD, bottom pin VDD or VSS. Okay. All thing done, then we'll press OK. We'll simply press OK here. All things are done, we'll press OK here. After pressing OK, we will come at this part. We'll able to see a block is there. Okay. We can rename it as an inverter. And we can put as an inverter here. And we can make it this one also IN. 1 second. 1 second, please. Let me, we can make it as an INV also. I think then we can change this design part also. We can, if we want, we can change this one also. Okay. We can change this part also, like this part. That block was there, square block. We can change like this to a inverter symbol. We can make it as an inverter symbol also, like this. Okay. We can make it as an inverter symbol also with this slanting line. Okay. This line. This is a symbol of an inverter we are creating. Okay. We are getting a symbol of an inverter. Let me make it proper now. I think it should proper. Then we can put this circle in front of this one. Okay. Okay. And then let me put it up till here at this level. Okay. So I think this inverter should be okay. So VDD, VSS, A and Y, all things are there. So this thing is done. This symbol, how we create a symbol, we this using these shapes, we can create a symbol. Okay. And then we will press save and we'll press save check. Okay. We have done the save check here. Okay. This thing has been done properly, and then we can close it. Like we can close it, and this one also we can close it. We will create a test bench for this one. We'll again go to the Bharat IC weekend. We'll go to file name and we'll create a cell view. We'll put here inverter underscore TB test bench. Okay. And press OK here. When we press OK here, a schematic window will open again. Okay. And then what we can do here is we will go to this device placement again instance here. We'll browse here again. Okay. We will go to our design, which is Bharat IC underscore weekend. Okay. And we have done the inverter already. We don't want this one. Sorry, 1 second. This is the inverter test bench. We want this inverter, the symbol we have created. We can see this symbol here. Okay. We can bring the symbol somewhere here and we'll escape and press okay. We can press this one here up till this level. You will see this block has came here actually. If you see, this block has actually came, and this is the inverter symbol. If you double click this one, you will able to see that schematic inside this one. Okay. You'll able to see that schematic inside this one. Okay. So this is how the symbol has been created. This one we will try to simulate. Okay. For the simulation, what we will do, we will click on this guy. We'll go to browse. We will take three things: one V pulse, one VCC, and one ground. Okay, these three things required. So for three things, we need to go to this analog library. Analog library, we have to go there. We have to write here vpulse. P-U-L-S-E, vpulse. Okay, vpulse is there. We can take the vpulse from here, and 1 second. Let me put the vpulse somewhere here. Okay. Then what I will do, I will go here again, and I will try to take a VCC. Okay, VCC. No, not this one. I need a VCC thing. Okay, where it is one. Let me check that where it has gone actually. It should be somewhere here. Okay, is that VDC? Sorry. But for me, it's VDC. Okay, it's VDC. I will put here the VDC. Again, I will go here. I will take a ground connection. Okay, GND. ND. Okay, ground connection. I will come back here. I will putting one ground here and one ground I should put here. Okay. Now I'll press if F for France. If you click on the keyboard F, then it will fit. Suppose your window is bit zoomed like this. You want to fit it, then what do? Just press F, it will fit the window actually. Okay. Now what we will do, we will first connect this guy to the inputs. Okay. We'll first connect this guy to the inputs here. Then again here. Then this should be connected here, and then this guy should come below and should be connected up till this level. Okay. This should be connected, and this ground I am connecting at this point. Okay. Now what I will do, I will put two pins. Input pin, like this is a input pin should be there. This is the A pin here, input. I will put an input connection here like this. It's a A pin. Okay, and I will click here, and then I will put an out pin. Sorry, Y pin out, which is our out pin. Okay, I will put it somewhere here. Okay, and I will try to align this one. Okay, after this one done, okay, we have to edit these parameters inside this one and this one. So for this one, I will click on this one. I will press Q for query. There are some of the parameters to be done. So actually, the simulation is not required for analog layout engineer. Okay, this is just to show you what are the options you can do inside a cadence virtuoso. Okay, from next class onwards, I will not do the simulation. I will just simply draw the circuit. I will go to the layout part. Okay, this simulation is actually not done in the analog. It's a part of an analog circuit design. Okay, in this one, I think someone is there. Like, who's this Suhel? Is it Pratyusha, your friend?
Yeah, sir.
Okay. 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 So we will be coming to this part. We have some couple of options here. Okay. We will start with the voltage 2. We'll start with for the B pulse, we will using the voltage 2. Our actual device is only for 1 volt. So we will consider here as 1 volt. Okay. We will not using any higher voltage, 1.8 volt or what. We will be doing it at 1 volt only. Then we'll put the period. These are random values I'm putting. Just we'll put the period as 20 nanoseconds. 20 nanoseconds. Then delay we will putting, you can copy these values, no issue. Delay 0 nanoseconds. Rise time we will be putting as 1 nanoseconds, and fall time as also 1 nanoseconds. Okay. Then the pulse we will putting as 10 nanoseconds. We'll put a 10 nanoseconds here. Okay. Okay, 10 nanoseconds. Okay. After these values, you can put here, you can alter these values required upon your simulation parameters. You can alter this one. So voltage to 1 volt, period 20 nanoseconds, delay 0, rise time 1 nanoseconds, fall time 1 nanosecond, and pulse width 10 nanoseconds. Okay. Then we'll press OK. This device is set. Now we'll come to this device and press Q. This is our VDD line, actual VDD line. This should be actually DC voltage. This should be actually 1 volt because our device is 1 volt device. Okay. We will put a 1 volt here, DC 1 volt. Okay. And okay, now then done. After this, all this parameter is set down, we can go to save and check save. Then we can go to launch ADEL. This is the analog like device simulation that thing. So we can go to this ADEL. In this ADEL, first go to this option AC/DC option. You can see here. Click on this one. You see a transient. First, we'll do a transient and DC analysis. Okay. For transient analysis, stop time we will put at 200 nanoseconds. 200 nanoseconds. Okay. 200 nanoseconds we will put. Okay. We'll put this in at 200 nanoseconds and give me 1 second. Give me 1 second, please. Please spare me 1 second. Okay. Okay. Done. So we will putting here as 200 nanoseconds actually, and then we will click this moderate option and press OK. Our this transit analysis has been done. Then we'll again click here. We'll put DC one here. Then we'll put save DC operating point here. Then click on this one and component parameter. For component parameter, what we will do, we'll click on this component parameter. We'll go to select component. For this one, we want to check. For we'll click on this guy. We'll get a this kind of multiple options. So we are the DC voltage. We'll see the DC voltage and press OK. We'll press OK. Then again, we will be see if you see here that it has been selected. Then we'll put the start time and stop time. Stop time should be like 0. Stop time should be actually 1 second. I've written the stop time. Okay. Stop time should be 0 and sorry, start time. One thing, stop time should be at 1. Okay. Start should be at 0 and stop time should be at 1. Okay. At 1 voltage. Okay. It will come at 1 voltage. 0 to 1 voltage. Okay. And then we'll press OK. Okay. After this one, we will be here. We are done here. Now we want where to plot. Which design way to plot? We'll plot between this A and Y, input and output. Okay. So do that one. We'll go on the simulation. So, okay. We go to output to be plotted. Select on schematic. Okay. We'll click this one and this one. Both we will click. And if we come here, you see A and Y has came here. Okay. This to be outputs as a plotted. After all this thing is set down, we will click this play button, green color. We'll click on this green color play button and it should start actually. Let me think why it is not starting. Let me check this. Okay. DKT error, unable to locate Spectre executable in the specified path. Okay. In this one, actually, Spectre is not available. Spectre Spectre round that thing is not available in this one. So if actually what is the problem here is the Spectre is actually not available in this system actually. Okay, in the system Spectre is actually not available. It should be with a memsim file. Okay, with a memsim file. If someone, I think I have deleted that memsim file actually from here. So I think in your system, whatever you have, it will run. Okay, actually, what the thing has been done here, I tell you what the issue has here. Okay, that in a cadence, if you check your files, you will see memsim is there for you guys. Okay. I have deleted that memsim intentionally because I don't require that simulation things actually in my system. That's the reason I deleted that memsim thing from my system. That is the reason it is not running that either memsim is required or spectre is required to run this simulation. In this one, I have deleted it intentionally because I don't do simulations. That's the reason I have deleted it. In your cadence, whatever you have that thing only there. I have deleted it separately. So you can delete that one with using RM minus RF. So you will be having that memsim thing inside your system. Don't worry for that one. So if you have, you can check that one. If you go to the Buett's home, go to cadence, you will able to see a memsim 151 will be there. With that one, you can simulate it. No worries for that one. That one is not available. So I forgot. Sorry very much for that one. I forgot that I was not having this one. Okay. So I think we can leave this simulation part. Okay. Hello. Hello.
Yes,
Hello.
yes. Yeah.
That the memsim is not available in my system. Actually, I have deleted it intentionally. So whoever has that, the what can I, that memsim can you can tell us that you will have the memsim in your system. You can guys can simulate because if I do it now again, it will take some time. Okay. I can do it, but it will take some time for me to again set up all sorts of thing and tell you. Okay. That is the issue I am unable to do. So let me first do the layout guy. Okay, so let me do the layout first. So then I will show you the simulation in next class. Okay, I will add this what called that memsim. I will add it in my system and I will show you the simulation part. Uh, Let this simulation be up till here only. I will show you. You guys have the memsim in your system. Don't worry. I have deleted it intentionally actually because I don't do simulation. That's the reason I have deleted it. So let me go to the schematic actually. So wherever we are. So up till here it is there. So excuse me. So actually that is the reason it is showing the virtuoso analog designer creates a UI that doesn't matches with the memsim hierarchy which is not available. Okay. Unable to look at Spectre executable in the specified path. That is not available. That is the reason I am unable to run the this simulation. Okay. So in this one simulation we unable to do. We set up the test bench. So test bench up till here it is okay. So if you see the test bench here, it's up till here it is okay. It is this can be simulated once we add the Spectre or the memsim in our system. We will able to start the then we will able to start the simulation. We can do the simulation. Don't worry. Tomorrow I will for sure I will show the simulation things. Don't worry for that one. Okay. So sorry for that one. I was not aware that memsim I have deleted from. That's why I told you to the simulation. Okay, tomorrow I will show the simulation. Okay, so this is the inverter schematic. We can go to the layout. For layout, what we will do, we'll click on launch here. We'll press here layout Excel. Simple layout Excel we will put here. Okay, and layout Excel I will put here. Create layout, create new configuration automatic. Okay, and press OK. And in this one, we'll press OK again here. Okay. We'll press again OK here. Okay. Then we will just put this one down here and we will come to this layout Excel editing. Okay. We'll double click this one, press F for fit the window. Okay. Then we will put here first when we come to this layout editor window, we will able to see couple of things. Like things are this is called a layer palette. This is called a layer palette actually. Okay. In this one, you will get multiple layer options: N-well, oxide, poly, P implant, N implant, metal one, via one. Many layers are there to design. Then comes your object in which you can freeze each of the shapes, vias, boundaries, many things you can freeze and to do your design as per your convenience. Okay. Some couples of things are at below actually. Okay, some couples of things are at below. You can see some options are below and that here also, and couple of options are at this region also. Okay, if you see here, some couples of options are at this part also. Okay, so these are many options here, like Ashura connectivity, like many things are there. We will come across each and everything. For bringing those device in this layout part, what we will do here is we will this guy generate all from source. This one is also here, and this you can get this in connectivity also. Connectivity generate all from source also. Here also you can get this one. Okay. All these are the couple of options here to do. But before starting the layout, one should do press E. E for England. Okay. Press E here. You will get a display options. This need to be fixed because this X snap spacing and Y snap spacing, why I am telling this one, let me tell you once. Okay. To do this one, I think we need to go to the GPDK 90 nanometer DRM. One second, let me type the GPDK. Sorry, GPDK 90. Okay, 90. Actually, here it should be somewhere. Okay. Okay, let me check this one. I think it should be somewhere here. Okay, that DRM. Kite. Okay, the DRM should be, I think I don't have the DRM here. GPDK 90 nm. Okay, I think that one I have there. Wait, let me check that one. SPC, I think I should have the GPDK somewhere here. Okay, exchange. No, not the downloads. I think somewhere it should be somewhere here. In this one, DRM actually it should be. Okay. One second, please. Let me take out that DRM thing from here. Okay, I got it. Got it. Okay. Let me put the DRM somewhere here. Okay. And I will put the DRM. Okay. This is the design rule manual for your, I will supply this one to you. So it will be before starting a layout, one should know the how to read the DRM, because reading the DRM is very essential to start the layout. Okay. There are a couple of things here. Okay, like layer informations, what are DRC rules available in the deck actually, what is antenna rule, what are the ESD rules, many things are there inside this one. Okay, so not to go in that part, I will tell you step by step. First we need here is these values, X snap spacing and Y snap spacing. What are these values? For that one, go to search here and type grid. GRID grid here. Okay, you will get a grid information. Default grid should be 0.005. Okay, because this parameter, if you don't set here, it is 0.005 and it is 0.01. If you don't set it now, you will get an error in the time of DRC. You have done all the layout and now you are getting an error of a grid. That's a very bad thing to be get in the time of DRC. If you are getting that one, you have to do the whole lot of rework again. You do the whole work from again starting from the scratch. That's a very bad thing will happen if you do like this thing in the industry. Okay, so for that one, press E and check what is the spacing, then come to the DRM and check what is the grid value. The grid value is 0.005. So we will make it as 0.005 here. We will edit, then we will get 0.005 here. Okay. After this all done, we will able to do, and then we will do press OK here. Then we will press OK here. Now, if you see, our screen is set to 0.005 grid pattern. All things are done. Now we can do here is we will go to all generate all from source. After clicking on this one, you will get this couple of options here. Many options are there. Generate IO pin, PR boundary flow, and we'll go to IO pins only. Okay. There are A, VDD, VSS, Y. Okay. So we will be changing these pins actually. We need to change these pins. Okay. So these pins are coming in poly, but this should be in metal 1 pin. It should be in metal 1 pin. Remember, all the pin by default should be in metal 1 pin. Wherever required metal 2 pin, we will put metal 2, we will make it manually metal 3, metal 4, whatever pin is required, we will make it manually. But default, you should make it metal 1 pin. Okay. Do that one, select this one, click here, go down below and search for the metal 1 pin. You can see this blue one, metal 1 pin here. Okay, available. Click on this one and update. Everything will change to metal 1 pin here. and create as label. If you don't select this one, the label over that pin, which pin is this one, you will only be able to get. You have to go inside that one. You have to check. So that's for better. Create label as label. Okay, you can make it as a label here. Let me make it as a Roman here only. Okay, I'm just making a Roman. Okay, you can do this Roman thing later also. Okay, and I'm making it 0.5 only from here. Like who's that? Okay, let me add him. Okay, so I'm just making it as a, let me make it as a 0.3. No issue. You can do it later also. This option you don't click here, and also you can don't required for the option now. You don't need. You can do it. Just click change to metal one pin, create as label, select label. Okay. After this all done, just click on press OK. We press OK, you will see the devices have been came here. PMOS 1 volt, NMOS 1 volt. Now you cannot see the layer. Okay. Okay. Before
Sir,
turning
I
on
have a
the.
question here. Like,
Okay. Then.
so,
Yeah. Tell.
so actually, like pins, yeah, pins are pins can be given in any metal, right? Like, let us
Any
say
metal, any metal,
pin.
any metal.
Can, so can we give higher metals like LB something like that, or we can't give like that?
Eat in the evening, like
I think someone's
7 o'clock.
mic is turned on. Yes, still.
Yeah, I mean, can we give in like top metals also? Like, let us say if I want to give in LB metal
Of
layer,
of
so
course,
can
of
I
course,
give
of
like
course,
that, or like?
No, you can give. You can give. Of course, you can give. You can see why we do
So,
it in default in a metal one pin, because sometime the basic metal is metal one here. Okay, here is metal one. Okay, so as per the convenience, we generally try to use less higher metals, because when we go to the higher metal, the cost of the fabrication increases. We try to do it in metal one itself only, if the possible metal one, maximum metal two. When we are going for a metal 2 or any higher metals, and for which the output or input pin to be placed, we will change that pin to that particular metal pin. So suppose I am here with a metal 1 pin now, and suppose I have drawn here, suppose a metal 2 track. Okay, this suppose is my output part. Okay, so what will happen, I will put this pin over this one. I will select this, first I will select this pin, as well as I will select this name also. Why? And I will press query on this one. I will click common. Separately also you can do. I'm doing it in a single shot only. Okay. Common as is, go here and make it a metal 2 pin and press OK. Actually, it should be. If you put a metal 1 pin over metal 2, it will flag the LVS error. It will not pass the LVS only, because it will not able to
yeah,
read
we
that
need to
pin.
keep yeah. Yes, yeah.
No,
So
actually,
one more
what is the
thing, like
thing?
let us
Yeah, tell.
let us say if you keep in like a metal one, right? Let us say it is IO pad. Okay, let us say it need to go to the external side. Okay, so from metal one to LB layer, we need to stack the each and every metal, and we need to give the wires for each and everywhere, like something like that, or like a.
Yes. Suppose if your IO pads is in metal one, suppose your IO pad is in metal 8. Okay, coming from
Let us
metal
say
8.
it. Let us say it is our LB layer. Let us say it is IO pad output is going to in the LB layer, for example.
Okay, okay,
So my
and
my
and
pin
our
connection
device
you.
has in and device is in, suppose, metal one. You are asking this question, right?
Yes. For let us consider an output driver for any TX system or something like that.
Mm-hmm.
So my pin is a pad pin, but it need to go to external side. So external
Okay.
side connection will be into LB layer, right? Mostly like a,
Then you have to go to that particular
which is
layer. You have to do stacking of that one. You have to do the stacking of the some metals from that metal one to the LV layer. You have to do the stacking there actually, because if that
but
is
if
an
you do
L,
stacking like yeah, one more question. Like if you do stacking, like capacitance will increase, right? Like capacitance at the pin will increase, right?
like why capacitance will increase, because if why the because capacitance increases, because when you are going to the higher metals, okay, actually stacking of metals create like it decreases. This means capacitor increasement delay will be there for sure. That is the
No,
reason why
resistance will decrease. Resistance will decrease, but capacitance will increase. Like as we go from like if you do stacking completely, But yeah, will we do like that in the practical or like my doubt is that one like so
I
let
got
us
it,
say
got
it
it,
is
got it
going
right.
the
I got your doubt. So either one thing you can do, you can do stacking of metals in that one. By stacking one metals, after doing the stacking of metal, that can one thing you can do. Someone's mic is turned on. Okay, so we can either we can do the stacking of metals, capacitance will increase because the resistance will be less. But one thing you can do, you can route that internal signal with a LV layer so that you can connect it directly without but one thing, if there is a delay coming, between the pad and the device, suppose if there is a, let me show you one thing in Paint. Like if there is a delay in between your suppose this is a pad, okay, suppose this is a pad, okay, and this is your device,
okay.
and the distance between them is suppose 100 micrometer, okay, and this is in suppose
Okay.
LV layer. Suppose this I am considering this as a LV layer, okay, so this is a LV layer,
Okay.
and here I am considering this as a metal one layer, okay, this is a metal one layer, okay, we have to connect this. So we have connected them, but there will be a delay because it's a routing, long routing, capacitance and stacking will be there. Of course, some other couple of metals will come, like metal 2 came suppose, then metal 3 came, then metal 4 came, like it came to up till that layer, okay. Then what we can do here is we can put clock buffers here. So we can put buffers here to decrease this kind of delays. At every like
But
20 microns, we
yeah,
can
but in
put.
analog, yeah, I got your point. But in like analog, at each and every point we can't keep buffers. So in that case, like we'll be going with the higher metals only, or to decrease the delay. Let us say
We
if there
can
is no
see, we
possibility of
can
keeping the
go.
buffers.
No, either you have to go for the higher metal, but delay will be there. So if somewhere you have to put the buffer, because without directly the buffer you won't be able to control the delay na. Because when there is a long routing between the pads and the device, if suppose the
Yeah, if
LV,
there is
LV
very
layer
long routing is there, yeah.
LV
Agree,
layer
agree,
concept
agree.
is
Yeah.
not there. If LV layer concept is not there, suppose we have drawn with a suppose metal 8 routing, because metal 8 is a very high resistive metal, so like very low resistive metal. So if we route it, suppose a 50 micron with metal 7 and metal 8, still we have to put the buffers there to control the delay. Otherwise, there will be a lot of delay from device to the pad actually. So either stacking of metal will be good, or we can put buffer for that cases. That is the two possible
Got it.
things can be done.
Thanks. Yeah, yeah, got it. Yeah.
So if place is not there, then we can do one thing, we can do some stacking of metals, but we have to find that place to put the buffers. Actually, I think it will be coming from the circuit designer only before starting of the floor plan, that you need to put the buffer at every 20 microns between the 100 micrometer.
Yes, yes. Yeah, yeah. Yes,
That
yes,
will be
yes,
there
yes, yes.
because it is already considered in the constraint part that this block should be the overall chip size, the whole die plan. This will be this, the buffer will be there, the placement of the device will this part, the distance between them will be roughly 100 micron. Then in each 20 micron we will put one buffer, so 5 buffers in every 20 microns. So then the routing of the each buffers, between each buffers, it will be 20 micron length. Then I think if you don't even do the stacking also, it will be okay. And if you are doing stacking, then it's also fine. Not a big issue it will be. Okay?
Yeah, yeah.
Okay, Mahesh. Okay, then this is the PMOS and this is the NMOS. Okay, so now if you see here, you cannot see the layers now. You are not visible the layers. Okay, for visibling the layer, press Shift and F. Shift and F if you press here, Shift and F if you press here, you will able to see these layers actually. These are the layers actually of the devices, okay? And this is your PR boundary, place and root boundary here, okay? And these are the pins A, Y, VDD, VSS pins, okay? So just simply select this device, clicking the left click, press S and bring it up till here. Okay. You can bring it up till here, this device. Okay. One thing you can do by this one, you can after bringing the device here, leave that one, don't need for that one. You can come here, you can press, you can select this device. Okay, and then you have to press O for orange, you have to press via M1 to poly via I will put here, and I will make it column 1 to column 2 here. Okay, and I will try to put it somewhere here. Okay, let me put it up till middle of this one. Okay, middle of this one I will put it here. Okay, I will try to put it here in the middle of this one. Okay, and I will check the distance of both the sides, because this need to be checked thoroughly. Okay, 0.07 this side, and this side should be roughly 0.07, so it's in the middle. Both sides should be same actually. Okay, if you don't put same, it looks very bad. Actually, the design looks bad and the delay can be there. So equivalent routing, matched routing should be there from the early stages. Okay, after this is done, you will see a notch type structure is presented, this part. Okay, so this can create DRC later. So this will create DRC at the later stage. If you come here, this notch can create a DRC issue. For that one, what we will do, we will go to this poly option. We'll press R for rectangle. Okay, press R, and what we will do, we will zoom at this point. We will left click, and we will try to join them. Okay, we'll try to join them like this, and again we will click on this one and we will try to join them up till this point. Okay, up till here, if you see, this part is complete, this via. You can do one thing, you can simply copy this whole thing, you can press C for copy, not control C. Here only C option works. You can bring it up till here, go to this guy here, and you can flip it simply from here. And then, so in one day it will not come, it you have to practice it sometimes, then it will come to you. Okay, then you will able to do it. Okay, then for aligning this, the device is up till here, then now click on A option, A for Apple, which is align. Just click on this align button, A, this symbol will come. Go here, you click here, it will become pink color, okay. Then you come below and you can press it up. Sorry. Then you can press it up till here. You press it up till here, you will see this has been aligned properly with respect to this one. You can draw it again also, you can just copy it. Better copying is not an issue for in analog layout. So you can just copy and reuse those things. Okay. Now this part gate connection is done. Many guys, what they do, they connect this gate connection directly from, let me show you, directly like this. You should not do this one because it's a very high resistive material. You should not do this one. That's the reason poly to metal one connection has been given to you. Okay, for that one you should be using M1 drawing here, M1 drawing here. From here, let's click on this one and bring it up till this part. Okay, and change this to like it is done here. Then you can go and this metal pin. So do the metal pin. What you will do, go to select on this metal one drawing layer, press P for Philippines. Okay, press P here. This kind of dot symbol will come here. You can click on, click on this part. You can go click on this part. Okay, go click on this part. Come, start drawing below. Put your mouse and end it up till here. Okay, up till here. So this looks like a proper connections. Okay, then you can do one thing. Okay, let it be like this. Up till here done, then you can do, you can select this device metal layer, press query Q, and then make it as 0.15. We are making a thicker width, a bit of thicker width we are keeping here. 0.15 we have kept here. Okay, after this all done, again we have to connect the drain connections. So how to do the drain connection? We will go simply here, we'll go to simply here. Okay, we'll go to simply here. We have connected the gate connection. Sorry, we have connected the gate connections. If we come here, the gate is getting highlighted here. This is the gate connection we have clicked. Okay, now we have to connect the drain connections. For the drain connections, what we will do, we will be, see the orange one is highlighting that this metal and this metal should be connected. Okay, that this metal should be connected. So this is the highlighted metal. Okay, you have to connect this one. To connect this one, metal one selected, go to this point particularly. Okay, and try drawing, press P and try drawing it up till this level. Okay, come below and end it up here. Okay, just for your change, you can just press Q and press, make it as 0.15. Bit thicker is good to do. Okay, it will automatically change the length. After this is done, you can decrease the size also if required. You can decrease the size as per the DRC rules. Okay, as per the DRC rules, you can decrease the size also like this. Okay, so I think it's 0.335 micron. That's couple of size is good. Okay, so, but when you want to put two metal to connection between this one, you have to keep a good amount of size. You have to put a good amount of. For now, I am not putting any metal to connection here. I will just put the pins here. I am not putting any metal to connections here actually. Okay, I'm just trying to make you familiar with the tool. Other time we will do those detailed routings. Okay. Again, we have to connect the source connection. To do the source connection, you have to select this part. You have to come up till here again. Okay, and again select this one query and make it 0.15. Okay, so many of the guys will not able to cope up today, so don't worry. Watch the video. Any issue you face, come back to me again. Practice 1 or 2 times. You practice, you will able to catch up this thing. Okay, so again you have to connect this below VSS part. Okay, so come here, select this one, bring it up till this part. Okay, just keep it up till here. We will do it. Select this one query and make it 0.15. Okay, after this all done, just try to put the whole thing inside this one so that it becomes easy for us. Okay, let me just increase this guy, and okay, up till here done. Now what I will do, so now if I run a DRC, I will get a latch up error. What is latch up? I will tell you later. So remove that one. We have to connect a connection here. We can just simply draw a metal one like this also, but we try to use like a multi-part path. That's called a taps. Okay. What I will do, I will go to create option here, multi-part path, MPP, and press FN F3. If you come here, you will able to see MPP template, new N-tap, P-tap. So for the P-type material, it should be, if it is PMOS, then you should press N-tap. And if it is N-tap, N-type, NMOS material, then you should select P-tap actually here. So this is how you set that one. Okay. So for P-type, for PMOS, it should be N-tap. For NMOS, it should be P-tap. Okay. So MPP template N-tap and press hide. Okay. And then simply draw it up till this length. Just simply draw it for now. Okay. It has been drawn. Then again go to create MPP multi-part path, press an FNF3 and make it P-tap now and hide here. Okay. You will just able to draw it like this up till this level. Okay. This level I'm not drawing it. Okay. Now what I will do here is I will simply take it up till this level. You will see a violet color line is also there, and this is also violet color line. So this is called a N-well actually. Okay, this is a N-well. So we need to merge this N-well. To do that one, select this device, press align A and click on this violet line. It will align it with this one perfectly. Okay. After this is done, see this thing is hanging outside this thing. So for doing this one, you will see an option called blue. This is called select option. Yellow it is now, it's a full select. You cannot, you will select, you will select the whole thing, but you want to increase it from this edge. or from this edge, you have to select on it this color blue. You will click on this one. So you can click on this one. You will able to decrease or increase from this part. Again, align and press align it here. Okay. Then again, I will try to align this one with respect to this one. I'm not going with the DRC now. I'm not going the DRC in for now. I'm just trying to show you. Again, click on this part and bring it up till here. I'm just trying to align it. Okay. 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 Let me do one thing. Let me align it up till here. We will draw anvil in the top of this one again. Okay. Let me draw it up till here. Okay. Done. Now for coming below this guy, let me align this one up till this length. Okay. And this should be a bit below because a 1 micron distance is required. I'm just keeping it. Okay. 1 micron is more required. Okay. One, because otherwise it will give a DRC error. Okay. I'm just keeping it. Try to keep the distance to check the measurement to bring the ruler. Press K option. K for king. It will bring the ruler. Click on one part and again do it will, you can see the orange ruler is coming. It's a 0.1. Okay. So now again, if I do here, I will try to bring it back up till this length. Okay. It is not come up till this length. Actually, it should come up till here. And then for this part also, I will try to bring it up till these dots. You can see these thin dots. You can see, I can try to bring it here. Okay. I'm just trying to make it like this. Okay. After this is placement is done this proper way, you can just press select this PR boundary again with align key like this and press align here. Again, click on this one, alignment, and then press align here. Again, click on this alignment and try to align with this respect. And this guy should also be aligned with up till here. Okay. After this is done, you will able to see this device is completed. Now if you see this device is not in origin, it's not in 00, you should be put it in 00. For that one you can put the, you can select the device, you can move those all things also you can do, but better easiest way to do, select sorry, go to this option, edit, advanced, move origin option is there. Go there, you will see the yellow marker. Go zoom at this end point and press, put it, align it here and press left click. Okay. It will come to the origin. Actually, the whole block will come to the origin itself only. Okay. Now you press save. Now you have to put the pins on the related metals. Okay. So for A option, this is our gate. So this is the input. So I will press stretch S option. I will press stretch here. Okay. I will click on this one. I will press S for stretch. Press S. This option will come. Just you can move it like this. You can move it like this up till here. Then again, you can move it up till this level. Just let me put it up till here. Let me take the Y connection here also again. Okay. Let me bring it up till here. Okay, let me bring it up till here. Then this is the VDD connection here. We will put the, this is the VDD. We'll put the VDD up till at this level. We'll put the VDD at this level and then we will put this VSS guy. Okay. We'll try to put the VSS guy here. We'll put the VSS guy here. But after putting all these things, you will see that letters are in colored white. Pins are okay. It's in metal one pin only, but the letters are in white color, text color. It should be also in metal color. This pin layer only this color should be. For that one, what I will do, I will go select this texts independently. I will go texts here, text here. Then I will press query and I will click this common. I will click this common option. This common option I will click here. And then I will go here below and I will select this metal one pin and press OK. If you don't do the common, only single will be done. If you do common, all will be done. Okay. If you see now, this has been changed to VDD metal one pin. Actually, if you see this one, it has been changed to metal one pin actually. it has been changed to the metal one pin, the text also, pin also. If you see now, your this layout has been completed for the inverter. Okay. Now, if you save this one, you will able to see this. It has been completed. You can now check the DRC and LVS thing. But DRC and LVS, I will show you later. So this is actually the overall how you can make a layout in a uh, in this like what I can say in this layout editor window. Now, if you compare this one with your this guy, this one, if you compare this one, able to see first two metal connections in the top and bottom. Okay, then come the P diffusion and the N diffusion. Okay, here the P diffusion is in red color and N diffusion is in N implant is in yellow color. Actually, it depends upon the technology to technology, but universally try to use this one. Don't try to use this one. Try using this one, these colors only. Okay, I'm just telling you, this is the red one is the this line is the P implant, and this yellow slanting line is the N implant. This is the N diffusion and P diffusion. Done. Then comes the drain connections. See, the drain connection has been connected here. If you come here, you will see the drain connection has been shorted and pulled out. Okay. So this has been shorted here and it has been pulled out. Okay. The drain connection Y. Now, if you come back here, you will see the source connection done from here. If you see the source connection coming and the below VSS also, VDD also done. Now the poly layer, it is connected. If you see here, up till here, poly is there. When we connect with the metal connection, see, we did a metal connection properly here to sort it. Okay. So this is how the stick diagram is very essential to understand, to align with the layout. Okay. So this is how we can do the layout in our layout editor window. Okay. Now you guys can ask me question if you have any questions. Hello. Hello.
Hello. Yeah.
Yeah.
Can we keep like all the layout related bind keys in one sheet, like so that it will be easy to refer? Like,
Yeah. Of course.
uh,
I have that one. Let me show you
sure,
that
sure.
bind keys.
Yeah.
I will share that one. Cadence hotkeys and bind keys. It is available for the schematic also. Schematic keys, which key you press, what the option will happen. And for the
Yeah.
layout also, if you come below, you will see the layout for what key will press and what will happen. That is also explained here. I will share it to you.
Sure. Thank you.
This is
Yeah.
this is the bind keys. It will be easy for you to understand the whole thing. Okay. Any other guys having issues?
Sir, in stick diagram, you have drawn the P diffusion, N diffusion, polysilicon, sir. Is there any way to draw like that, sir?
Like how? Can you repeat again?
In stick diagram, we have drawn this P diffusion, N diffusion, polysilicon layers, polysilicon
Uh-huh.
layers, no, sir.
Uh-huh.
Means, is there any way to draw like that, sir, or directly?
No. If you draw in like that, it will occupy lot of space. So that's not a correct way. So that's just only for understanding that stick diagram. Actually, if you come to the layout should be more optimized. Okay. If you see these blocks, this device what you click that is called P cell, parameterized cell. This has been drawn by some of the engineers in the industry. Okay, analog layout engineer only is responsible for this kind of work. So it's a turnout of a analog layout engineer. So someone, they go to the PDK design. In the PDK design, they will be doing this kind of parameterized cell design. In that one, they do this one. So how you have done in the stick diagram, so don't try to draw it in the layout. It will take lot of space and the parasitics will be very high. Okay, so that's not actually the way to be done. But in the stick diagram only, that is okay, stick diagram. But in the layout part, when you come, it should be optimized actually. Okay. I could have kept it somewhere here. I could have drawn this one with polysilicon. So that's not the correct way, na. So the layout should be up. What is the thing? When you are going to the market, okay, to buy a processor of your computer for I think for a i5, it will cost you 40,000. INR. Okay, so for 40,000, if the designer creates that kind of stick diagram based design, then the chip size will be bigger, then the die size will be also bigger. Then they will, in part of 40,000, they will ask you for 2 lakhs rupees. Will you pay for that i5 processor 2 lakhs rupees? Is it any sense of paying 2 lakhs rupees for a i5 processor? 40,000 is fine, because how that 40,000 has came by decreasing the nodes, that nodes, that when it's going when it is being like optimization has been done properly, then die size is less, the cost of die size is bigger, then it will go to more and more money you have to pay. So that is the reason the die size should not be bigger. That's the reason optimization is required here. You will see in low power design, who all know physical design things, in low power design there is a called optimization techniques. In physical design you will see a genus tool is there, cadence genus. In that one, the files are optimized properly so that they can be placed very properly in the PNR tool like Synopsys, ICC2 or Cadence Innovus. Okay, in that one they can be done properly, or in Virtuoso you use the analog layout, so that we can put optimized thing should be there. So it should take less space, and it should not violate the DRC rules. That should be the goal of an analog layout engineer. The floor plan should be compact, optimized, delay less means less delay, less parasitics, as well as it should be cost effective and economical. This should be goal of an analog layout engineer. Okay, so you cannot you should not do in that way. If you can do whatever, wherever you can just put these blocks. Say I'm showing you, let me do one thing, let me put one block here and block here. Then you can route it like this also you can route it. Okay, okay, let me take it up till the top. We can route it like this, we can route it like this, then we can bring it up till here. Then we can put one metal connection from this part to that, but I'm not putting the vias now here. Then we can do the connection like this also, we can put the connection like this also here. Then we can put one metal connection in the top, metal connection in the bottom. Now we can put this connection from here to here. One second.
Sir,
Yeah, tell.
in stick diagram, means how to draw that stick diagram, sir? Directly drawn all layers, no, sir. Is there any way, sir?
No, no,
Stick diagram.
just just remember this circuit diagram. If you see the circuit, it is correlating with the circuit. You can see the circuit and see the circuit and see the stick diagram. Is it correlating? Gate in the left side, output in the right side. This P diffusion represents the PMOS, the N diffusion represents the NMOS. It has been done as per the schematic thing, not as per the layout thing actually done. If you have problem, then tomorrow I will tell you again the stick diagram. Don't worry, Arshad. If you see the stick diagram, it is done as per the schematic thing, not as per the layout thing. Okay.
No, sir. For this one,
You can ask.
for
You can
stick
ask.
diagram,
No.
there is a steps, no, sir. How to draw stick diagrams
Like steps are there, na. First you will draw the first you will draw the
which are
metal
shorted like that.
connections. Yes, first you will draw the metals. First to draw is metal connection. Metal 1 and metal 2. Okay. Let me do it for again to you. It will be, I think, it will be easy for you to understand. Okay. First we will be drawing. Can you close the mic? Let me draw it for you. Okay. First step, draw two metal connections. Okay. Draw to, wait 1 second. It should be, okay. Draw two metal connections like this. Okay. In between this, we will draw. Okay. We will draw two metal connections like this and like this. Then we will come to our P diffusion first. We will make a P diffusion here. We'll make a P diffusion here. Then we will make a N diffusion at the bottom. We'll make a N diffusion here. Then again, we will try to connect these guys. We'll try to connect them actually. Okay. We'll try to connect them like this. Okay. Try to connect them. Then we will try to connect them, which is our Y output. Okay. Then what we will do after first step one, metal to be drawn, this kind of metal is VDD, and this VSS you should draw. Then you will draw this diffusion, yellow color with P diffusion, green color for the N diffusion. After the diffusion done, then you will connect these two diffusions with the metal connections, okay, for making the output. Okay. After this done, you will draw a poly layer. You will do a poly layer like this, okay, red color on top of this one, and one bottom in the top of the end diffusion also. Okay. Then what you will come below, you will come to this part again. You will make it again blue color, means you are connecting these two polys. You're shorting these two polys, okay, as we have done here. If you see here, we have connected both the gate connection using one metal one connection, okay, metal one layer. Okay, so that is the only I'm doing here, metal one connection. And then you can pull this outside and you will make it a type. So this should be the last step. So this should be the step one. Okay, so this should be your step one. Then this diffusion design should be your step two. Step two. Then this design, this connection between the drain and drain should be your step three. And then drawing this poly layer and connecting this both poly layer with a metal connection should be your step four. Step four. In between step 4 and step 5, you can make a inverter whole stick diagram. Okay. So this is you should follow. Okay, Arshad?
Okay.
Just see, when you are a very fresher, then only interviewer might ask you that stick diagram things. When you become experienced, no one will ask you stick diagram. Like very rare someone asks stick diagram. On that time, they will put you questions like what is floor planning, what is placements, what is EMIR, those kinds of big questions will come. Okay. Okay, so any other questions?
So I have one more question. So let us say if you see the current layout, if you see our current layout, we are having like a poly direction in the vertical direction, right? So let us say like so poly direction is always be vertical. Like let us say we are having a H version cells and V version cells, right, in our library. So
what library? Repeat again.
In our any IO library or something like any particular library, so we'll be having a northeast and a northwest direction cells, right? Like H version and V version cells.
Okay.
So for always poly direction will be vertical in both directions, or like poly direction also will be in horizontal, like how it
no, poly
decided.
cannot be in horizontal. It should be in vertical only, because every PDK follows the vertical only for the poly.
Okay. So
Because
always poly direction in the only vertical only. So
poly
either you
direction
do the
should
H
be in
version.
vertical. Yeah, tell. Repeat again.
Okay. So, but in case of like both H version and V version, schematic will be same, but only like layout will be different. Like so, in order to have a like a same poly direction, but we'll be having a different pin locations. So that's why we need to do the different layout, something like that, or.
No, the poly direction everywhere it should be vertical. Okay, if you see the fabrication of the cross section of the MOSFET, you will able to see the poly is in vertical only. You will see that poly is in horizontal. Okay, because poly is not drawn in horizontal, it should be in vertical. Metal connections can be metal's connection has orientation. If it is even metal like metal 2, 4, 6, then it should be in horizontal. If it is odd metal, starting from metal 1 onwards, it will be metal 1, 3, 5, 7. It should be every time in vertical direction. But only metal 1 has an exception of omnidirection, but for very limited point. Like if you are drawing, if you are drawing
direction.
Yeah, tell.
This metal orientation is there is no particular rule, right? We are keeping just to minimize the like routing, right? Like so vertical and horizontal.
No. Vertical horizontal is from the DFM point of view, design for manufacturability point of view. This orientation is there. So only
Okay.
if
Okay.
you go to very lower nodes like FinFET nodes, this
Mm-hmm.
omnidirectional metal one is also not there. Metal one should be in vertical itself only, and metal two,
Okay.
metal and odd even metal should be in horizontal only. But in the higher nodes, if you come back, you will able to see that metal one, like suppose 1 micron of distance you are routing or 0.5 micron, that part you can do with metal one horizontal also. But if you are going for a long routing like a vertical, you should every time use metal one vertical only. Try to keep the even metals in horizontal and odd metals in vertical. Ignore such kind of routing where what will happen, I tell you. Suppose you have drawn a metal one in horizontal and vertical both. Now you have to pass another metal one. Then you will have a congestion. Then you will have to. Then will be a short will be there. That is the reason horizontal vertical has been made, so that it is easy to route that particular point, that you can cross over each other. That is the reason it has been made
Okay.
like that.
Got it. Okay. Okay.
Okay, okay, Mahesh. Yeah. Any other questions?
Hello.
Yeah, Rohit. Tell me.
Yes, sir. I'm a little bit confused over here. Can you go to the tool?
Yeah, sure. Here.
Yeah. Oh, no,
Yeah,
oh,
tell.
not to the layout. Yeah.
Let me delete this one. Yeah, tell.
Yeah. I didn't really get. I mean, we used to draw layout from the scratch from JX layer to J, from starting from JX layer, and I'm coming to the RX layer,
Uh-huh.
and after that we have to deposit the polys, and after that we will metal route it, and
Mm-hmm.
we'll connect it. Obviously, we'll connect it with the via I mean to the metals to RX layers.
Okay.
And I didn't see, I mean my style of, I didn't see the, I wanted to see the the poly vertical poly layer, which runs from PMOS through NMOS. Where was it?
So this is the poly layer for the PMOS. This is green one is the layer for the NMOS. If you take this device out, let me take this device out. Okay.
Mhm.
And let me select this one. Let me flatten this device. Okay. Other guys also please see. Let me flatten this device. Basics hierarchy was I will go flatten, and I will flatten P cell. Okay. If I flatten it, you will able to see each and every layers. Okay. In this one, you won't be able to see the layers. Now you can select the layers. Okay. Now let me select each of the layers here. Okay. Now let me select each of the layers at this point. Then this is your oxide one. This is your gate oxide. This one. Okay. So now you come to your poly layer. Okay, now let me keep it here, and this one should be here, and these guys, this contacts. Okay, this is the same thing again repeated. Okay, now if I come here, this is the NVEL. If you select and
Okay.
press query, it will be NVEL layer. Okay, then if you come this one, this is a P implant. Okay, this is a
Yeah.
P implant layer. Then this red one, this is the gate oxide. So this is the oxide layer actually. Okay. Then this green one, if you click and select, it's the poly layer, which is running in between this one. Okay. This is the poly layer. Then if you
So
come in this, yeah, tell.
what was the width of it? I mean, is it
Wait,
90 nanometer or
points,
60?
we selected 0.6 like this in
Okay.
the length one, 600, that one we selected, and in this side we selected 900. If you
Yeah.
go and this device and select Q, you will see the parameter 600 nanometer by 900 nanometer, which is 0.6 micrometer by 0.9 micrometer.
Yeah, yeah, I got you, sir. But the thing is that can't we directly deposit, the poly entirely through NMOS and to, PMOS,
like
PMOS through
like
NMOS?
you want to do it in this way, like if I'm not wrong, you want to do, suppose I'm drawing it like this, you want to draw it like this
Yeah,
directly, right?
yeah, yeah,
No,
yeah,
no,
yeah.
no, no. I got your point. I already told you this is coming by default, this length. Okay, this length, up till this length, it is coming by default. Okay, this length here coming by default. We are adding this one is actually a via, a poly to M1
Yeah,
via this actually. Okay, Again, if this poly material is a polysilicon material that has very high resistance material. If the resistance is very high, then as per the Ohm's law, voltage will obviously drop. It will drop or not. If it's V is equal to IR, then V is equal to I. Suppose if current is 1 milliamp and resistance is higher, then voltage will of course drop. So that is the reason we don't route the poly to poly using only a poly connection. We could have routed it like this also. Okay, rather in place of metal, we could have routed like this also, but this should not be actually done. It's actually a wrong technique to do because it's a very high resistance material. So when there is a sensitive blocks are there, like ring oscillators, then other delay which has a high extreme delay constraint blocks are there, it will create a lot of delay. If you can do one thing, you can draw one layout in both the cases. One you can draw with metal one you can draw with poly. Okay, then do a parasitic extraction and then do a post layout simulation. Okay, both the blocks. And with suppose in the schematic, if you are having a value A, you will see the metal one having suppose value of a 0.1, but the poly one which you are trying to say, it will having a value of a1 like a 0.9. That value will gradually increase due to the high level of parasitics and delay will increase. You can check that one. That will be a good learning for you. Or I will show it in some other class, that when we'll do the parasitic extractions, I will show you that post layered simulation thing.
Yeah. One more thing as well. So aren't we using the metal 2 for the output?
We can use, of course we can use, but we didn't use there. We can use. So let me delete it. Let me go in this metal 2 track. Okay, this metal 2 track here. Okay, I can just simply draw it up till this length and excuse me, let me make it 0.15. Sorry, 0.15 here. Then what I can do here is I can go O option. I can go to M2 to M1. I can make it this via. Okay, this enclosure of the via is minimum 0.26. So we have to put a metal of 0.26 width only. That is the reason I don't made it. So other guys will get confused at this moment. So that is so for that one, you have to calculate the length actually. You have to actually calculate that overall length. So suppose if I am considering this as a 0.26, okay, 0.26 I'm considering this one. So I have to put this in somehow in this space. This space should be minimum 0.2 for me. Okay, let me make it as 0.2 for me. And then let me pull it down up till this length. Okay, this space. And then again, this space should be at least 0.12 for my side. Okay, okay, let me do one thing. Let me first select it. Okay, let me first select it and let me make it like this. Okay, 0.12. Okay, sorry, it should be 0.12 from here, not from the top. Okay, let me make it 0.12 distance minimum. Okay, I think that's 0.1 only. Okay, then the DRC will actually not come. Okay, now what I can do here is, now I can put a M2 to M1 via at this level. I can put a M2 to M1 via at this level, and you can increase this size also to 0.26. I think you can increase this 0.26, this one, and then this one also you can make it 0.26. Okay, but you should maintain the space between these guys. Okay, you should maintain the space between. It should be 0.2 minimum. I think 0.15 is the minimum. So let me do one thing. Let me align this one with respect to this one. Okay, let me align it up till here. And then what I can do here is I can simply take this guy up till here and I will put it at this level, and I will simply make common and I will make it a M2 pin. You are asking now, Mahesh, so like this kind of thing we can have to do. We have to change these two metal to pin orientation. And then again, I will simply copy this guy. This guy, I will copy it and I will place it again here at this level, and I will try to squeeze this one back up till this level, and I will try to put one again this kind of track here. Okay, then again I will simply draw it up till this length, and again I will simply take these both guys. Okay, let me take both of them, press query common, and I will make it metal to pin. Okay, and press OK. Now what I will do here is, okay, let me decrease it a bit. Okay, let me decrease it a bit. 1 second. Okay, let me put it somewhere here, and then I will simply put it up till here, and then I can align this PR boundary with respect to this one. Okay, with this one I can align it with this one, and this guy I can align with respect to this one. Okay, this is how you can put this output also. No issue. You can put it.
And what about the offset? Offset has to be, I mean, 0.13, right?
This one fixed. Okay, that offset means you are asking about this one, X snap switching and Y snap switching. Hello. Hello.
Yeah, offset is nothing but, I mean, I'm just asking about, yeah, I'm just asking about, the output, the distance between the output to the end of the cell, or the input to the end of the cell.
No, actually we haven't calculated that one. This one you are asking, right?
Let me just see you. Yeah.
What you're trying to ask?
No. From the output to the end of the, from the contact to the end of the cell has to be 0.13, right?
This one, right?
Yeah, 0.13 or 0.39.
That should
Since
see,
it is,
that's actually a different calculation. I think you are calculating the delay calculations point of view, right?
no. I'm just calculating in the point of view of this offset. So offset,
Okay.
I mean, since we are using the pin pitch as 0.26, so I mean, offset has to be, it has to be, so in order to match
Got
the
it,
two
got it.
cells, it has to be, yeah,
Got it.
0.13
Got
or,
it.
yeah.
Actually, we didn't calculate such things here because it's just a today first class of the layout. Na? That's the reason we haven't calculated. Actually, if you ask me, as per standard cell design, this is not a correct design. Okay, it's just to make everyone familiar with the tool. If I today go with all sorts of huge techniques, other guys will be confused. Many of the guys will get confused. That is the reason I didn't took the many calculations I didn't took, because actually this thing, see, if you see this one, if you run the DRC, you will get an error. Actually, you should get an error in this one.
Because of the offset, obviously there'll be error.
Because this is not proper actually. If you select this, select this guy. If you select this guy here and sorry, I think okay, select this guy, press query and subpart. You will say offset subpath here. Okay. So if you have to align this NVL properly, otherwise you will get a DRC error for sure. I know actually it is a DRC error will be there. Actually, we have done it to make them familiar with the tool only. Okay. So if I make everything a single day, then it will be very heavy for the guys to understand.
Okay.
Okay. Got it.
Can you please help me out with this tool so that I can, work on the inverter at least to make sure
Okay.
that it's
Sure.
proper. Yeah. Let me just share my screen so that
Let me turn off the recording actually. I
yeah,
think
sure.
let me turn off.
And if anybody has doubts, then yeah, I'm sorry.
Stop recording. Okay, the recording will be available.